Okay, let's begin today's lecture. Actually, today's agenda is that we have to discuss the diode behavior model. Actually, behavior modeling of semiconductor devices is important because we can analyze them in circuit design. So we start with the introduction of semiconductors. So you know that the most of the semiconductor devices are made of silicon and silicon found in abundance in sand. And the intrinsic silicon contains almost 1.1 into 10 raised to power 16 carriers per cubic meter. And that concentration will be doubles for every 11 degrees centigrade rise in temperature. So actually, pure silicon cannot behave as a semiconductor material. So we have to add some impurity, which is called the dopant, and it can be pentavalent. And we have the pentavalent impurities is phosphorus and arsenic. They have 5 electrons in the outermost shell, and they form the N-type material. So the concentration of holes in the N-type material is in fact is equal to the number of impurity atoms added into the intrinsic silicon. So the concentration of free electrons in N-type material is in fact is equal to Nd. And if we have to calculate the number of holes in N-type material, that would be Ni square by Nd. Nd is in fact is the donor concentration or the dopant concentration. So similarly, we have the p-type material, and in p-type material we have the boron impurity. So boron create the excess of holes, and if you want to calculate the number of uh, holes in the p-type material, that would be Na. And if you want to calculate the number of free electrons in the p-type material, that would be Ni square by Na. Actually, the doping concentration is in fact is represented in light doping to intermediate doping to the heavily doped materials. And if it is lightly doped, so we represent it with the negative sign. So we have lightly doped p-type and n-type materials. And we have p and n-type materials which are normally doped. And we have the p plus and n plus materials which are heavily doped. So the concentration in the lightly doped material is 5 into 10 raised to power 21 carriers per cubic meter. However, the heavily doped material have the charge carrier concentration of 10 raised to power 25 to 10 raised to power 27 carriers per cubic centimeter. In fact, we have considered a single-sided PN junction, and in a single-sided PN junction, one side is heavily doped, right? Which usually have the aluminum contact, and the other side is comparatively lightly doped, called the substrate or well. So if you see this diagram, so the P plus side is heavily doped, and we have the aluminum contact here, and this is in fact is the N side, which is lightly doped, and this lightly doped side is in fact has called the substrate or well. So this side, the impurity concentration is Na. This is in fact is the p-type impurity, and this is in fact is the pentavalent impurity Nd. So the important thing to remember here is that the width of the depletion region is in fact is large at the lightly doped site and small at the heavily doped site. So in fact, due to the improper concentration of electrons and holes, there is the mobility of the charge carriers, and this mobility of charge carriers will form this depletion region, and the width of the depletion region nxn at the n side is larger, and width of depletion region at the p side is smaller. So this in fact is inversely proportional to the doping concentration. So if the doping concentration is heavy, so the width of the depletion region at this side is small, and if the doping concentration is light, so the width of the depletion region is larger at this side. So finally, there will be an electric field created which stops further mobility of the charge carriers, and this electric field opposes the current, diffusion current, and this will stop further movement of charge carriers across this depletion region. So we have to see that the potential of this electric field is represented by phi naught, which is Vt natural log of Na Nd divided by Ni square. So if you substitute the value of Vt is 26 millivolt at 25 degrees centigrade, and if you want to calculate it for other temperatures, so you can calculate it for other temperatures by substituting Kt by Q, and you have the value of K is 1.38 into 10 to the power minus 23 joule per Kelvin, and Q is 1.602 into 10 to the power minus 90 coulombs. So now let's see that the width of the depletion region XP is small compared to the depletion width at the N side. And the reason I have told you that the P side is heavily doped, so XP is small compared to XN. So we can have a look over the relationship. So the width of the depletion region at the inside is 2Ks epsilon naught phi naught by Vr by Q, and the doping concentration is divided by N plus Nd under root of the whole relationship. Similarly, we have the relationship for the width of the depletion region at P side with this relationship. So here we have the values of this constant, that phi naught is the permittivity of free space. Ps is in fact the relative permittivity of silicon. And phi naught is the built-in potential of the clone junction, and Vr is the reverse bias voltage. So the width will be increased by the reverse bias voltage. So this XP is the function of the reverse bias voltage because all other terms are constant in this relationship. The doping concentration at P and N side is constant. So N, A, and D is constant. So we take Na greater than Nd. So, but the value of these doping concentration is constant, and similarly Ks epsilon naught and Q is also constant. So we have, in fact, is the only thing which we need to change is the reverse bias voltage. So the reverse bias voltage will affect the width of the depletion region. So we can simplify this relationship if we take the value of Na is much larger than Nd. So this term is approximately Na, and we have the approximate relationship of this is 1 over Nd, and this is Nd, and this is approximated as Na. So this is Nd by Na square. So we have the approximated relationship for the depletion width, and when we take the ratio of these two regions, Xn over Xp, so we will have the Na by Nd. So it means that the width of the depletion region at N side is inversely proportional to Nd, which is the doping concentration at the N side, and this is in fact is Xp is inversely proportional to Na, which is the doping concentration at P side. Now we have look into the charge, the total charge at Xp Q minus at both P side and N side is constant. So the charge is constant. So how can we calculate the value of this charge? So we multiply the total immobile charge carriers into the depletion width, and total immobile charge carriers is in fact is equal to the Q times into the doping concentration. So this is Q times into the doping concentration, and we will have this depletion width. So this depletion width, when multiplied by the total immobile charge carriers, will give you the value of total charge. So you have this Q and D terms cancel with this Q and ND term, and you will have this simplified relationship. For approximate relationship for Na greater than Nd, so you have these two terms will be cancelled, and you have only Q and D multiplied by this term, and you will have the value of Q positive. Now you can see that the depletion capacitance is in fact is the function of the reverse bias voltage, and differentiate this charge with respect to the reverse bias voltage. So you will get the value of this derivative, and the value of this derivative is given by this relationship. So by taking the derivative, we will have the simplified relationship, and this relationship represents the value of the depletion capacitance. We will interpret this relationship in a simplified form, and this simplified form of this relationship is if we take the value of Cj naught. So this constant term is in fact is Cj naught, and the approximated form of this is in fact is Ks epsilon naught Q and D divided by 2 phi naught under root. So this Cj naught is divided by 1 plus Vr by phi naught under root. So this is the value of the depletion capacitance, and that relationship is very important, and we use this value of depletion capacitance for any PN junction in further studies. So this is the one parameter which we drive for the diode, which is the depletion capacitance. So if we go further, so we can have this relationship. We know that this is the total charge, and this total charge is simplified in this form. Then you multiply it by 2 phi naught under root and divide it by 2 phi under root. So you will get the value of this relationship is equal to 2 phi naught Cj naught 1 plus Vr by phi naught. So this is also an important relationship for the charge. So you can express charge in terms of the capacitance when there is zero reverse bias voltage. So this is the derivation for abrupt junction. So when there is an abrupt junction, so there is an abrupt change in the PN junction. So, but there is also the graded PN junction in form of BJT, and the value of this 0.5 constant is in fact is replaced by 0.6 or 0.7. So we have the value of this mj is equal to 1.3 for linearly graded junction, and this is called the doping profile constant. And this Cj is in fact is expressed in the form as we only replace the term, the exponent value, and the rest of the expression is same. Similarly, we can write it as Cj naught 1 plus Vr phi naught Mj. So this is an important relationship. So next, for the charge, we can also have the simplified relationship for the graded PN junction. Large, for example, we have an abrupt junction, and there is a large change in the reverse bias voltage. So in fact, we cannot calculate the value of the charge throughout the junction, but we can calculate at 2 points, say point 2, the endpoint and point 1. So it will be just like you just grade it into values V1 and V2. So this is the voltage difference, and this is in fact is the charge carrier concentration. And you know the value of the capacitance is in fact is Q by V. And if we apply a signal which is of high value, so we will have the change in the charge carrier concentration divided by the change of voltage. And we have derived the relationship for the charge carriers. If we substitute this in this relationship, so we will have 2 Cj naught phi naught, and we have the difference of two terms, 1 plus V2 by phi naught under root minus 1 plus V1 phi naught under root, and we take the difference of the voltage V2 minus V1. So this is all about the depletion capacitance. So we model one parameter of the diode, which is the depletion capacitance. So there are a few other parameters which we need to find, and for this uh, we have to see the uh, total capacitance is in fact is the diffusion capacitance plus the depletion capacitance, and the diffusion capacitance is in fact is much larger than the depletion capacitance, and we approximate this total capacitance as the diffusion capacitance. So because the value of this junction capacitance is approximately 2 Cj naught. So this approximation doesn't matter because the value of CD is very high. And what is the value of CD? So the value of CD is the transit time of the diode, the diffusion current divided by the VT. And we see that the diffusion capacitance is directly proportional to the diffusion current, and that value of diffusion current is in fact is given by this relationship. So this is ID is equal to IS EVD by VT. And the value of IS is defined by the doping concentration and the length of depletion region at N and P side. So this is in fact IS is in fact is the scale current, and ID is in fact is the diffusion current, and VD is the forward bias voltage applied across the diode. So this is about the capacitance. So we have the total capacitance CJ and CD. So they are in parallel if we sum these two capacitance value, and we have the resistance of the diode, which is modeled as RT. And how to model the resistance of the diode, because it is in fact is a function of the current with respect to the voltage. So that is equal to 1 by RT. So you can take the derivative, and you will find the value of dID by dVD is equal to ID by VT. So we can substitute the value of these capacitance and CJ and CD and RD in this model, and this is in fact is the behavior model of the diode. So that is important when you have the small signal analysis. You can use this model for circuit analysis. So now actually we go on to the MOS transistor, because this is the first step we have done. In this step, we have covered the behavior model of the diode. Now actually first we study the MOS transistor, because The last 40 years is in fact is the era of CMOS, and we have in fact all the circuit designing in integrated circuits done by this CMOS. So the MOS circuits, in fact, is also like other transistor is a three-terminal device, and fourth terminal is not electrically connected, and that is in fact is the body of the transistor. So three electrical terminals are source, drain, and gate, and in fact. Gate terminal is just to turn on and off the transistor. So for NMOS, we have the positive gate voltage and to turn on the transistor, and for PMOS, we have the negative gate voltage to turn on the transistor. So the length of the transistor is from source to drain. So for a typical NMOS transistor, its length is around 28 nanometer. The PMOS and NMOS are interconnected with each other to form different logic gates like NAND, NOR, AND, OR, etc. So in a typical NMOS transistor, current conducts from drain to source. So the drain terminal is positive compared to the source terminal, and the current flows from drain to source, and that is in fact is the drain current. In PMOS, in fact, the current flows from source to drain. Actually, in fact, the source and drain is physically same, but the only difference is the voltage applied at the drain is positive in case of NMOS, and in case of PMOS, the positive voltage is applied at the source. So the gate is normally realized as polysilicon material. So uh, this actually have a very high resistance, and uh, this helps to make the transistor switching faster. So the thickness of the gate is 1 to 30 nanometer. So actually, uh, in later technology, we replace the gate with the metal contact, and we want to uh, we want that uh, the thickness of the gate will be further reduced. So these are the, in fact, is the symbols for N-channel transistors, and these are the symbol for P-channel transistor. The most common of which is the A part, and this A part is most commonly used. Other symbols are not so common. In SPICE, we use this C and B type symbols. So now we see the functionality of this N-channel transistor. In N-channel transistor, we have initially the source and drain are ground, and this source and drain are heavily doped N-type materials. So This in fact heavily doped n-type materials, and the body or substrate of the transistor is lightly doped p-type material. So I'm just talking about n-channel or NMOS transistor. So you know the gate voltage would be uh, positive to turn on the transistor. So initially the gate voltage is less than zero, and there is, due to this negative voltage, there is the accumulation of negative carriers here, and we have the positive carriers here. So when we apply the gate voltage, which is greater than zero, so when the gate voltage is greater than zero, so this is the inversion of the charge carriers. So this, in fact, charge carriers is in fact positive, and this is in fact is the negative charge carriers. And the depletion layer here with the PN junction and air across the drain, this combines with this area and forms a channel from drain to source. So this accumulation of negative carriers will form a channel from drain to source. And if you apply, so there is in fact we further increase the gate voltage to further increase the gate voltage so that the concentration of holes in this substrate will be equal to the concentration of negative charge carriers in the channel. So the point where these two concentration are equal is called the threshold voltage. And when the VG voltage is further increased than this threshold voltage, so this will cause the conduction of the current uh, from drain to source. So the value of this current, the drain current, is in fact is represented by this relationship. So this is in fact is the mobility of the free electrons μL and the total charge carrier concentration QL W by L into the drain to source voltage. So if we substitute the value of Qn here, so the value of Qn is in fact is Cv, and Cv is in fact is C VGS minus VTN, and VGS minus VTN is Vm. So this CVm is the value of Qn, and we have represent the value of Qn is COX PF, and this is in fact is the value of ID current. So there is a point we apply the voltage at the drain, and we keep increasing this voltage. So there will be a pinch of point near the drain. So this is in fact is just like the pressure point, and it will not allow the increase in the value of ID. So the at this pinch of point, the value of ID will remain constant. So the concentration of carriers near the drain will be less compared to the concentration near the source. And you can find the value of this gradient when you have the charge carrier concentration varies from CBF to CVGT minus VTN. So at any point through the channel, you can find the value of the charge carrier concentration with this relationship. So the important thing is that this value of ID when VDS is equal to VF. So this is in fact is the point where we have the pinch of occurs, and we can further simplify this relationship by substituting the value of VDS here, because this point VDS is equal to VF, and you can find this curve as ID is in fact is less than equal to mu n Cux W by L VGS minus VTN by into VDS. So what about this value of COX? The value of this COX can be found by this relationship because in fact the capacitance of the oxide layer is in fact is dependent over the parameter QX, permittivity of the silicon dioxide, that is the permittivity of free space, and that is the thickness of the oxide layer. So if we know the thickness of the oxide layer and we know these two parameters, so with these two parameters we can find the value of COX. So by calculating the value of COX, you can find the total charge at the inside, and this is in fact is equal to the gate capacitance into VF. So this Q is equal to CV, as we have seen it previously that this in fact is the gate capacitance into VF, and VF is equal to VGS minus VTN. So this gate capacitance is in fact is the area of the gate into the capacitance of the oxide layer, and this is in fact is WLCOX VF. So by calculating all this, we can simplify the relationship for ID, the output current, and the output voltage. So VD, ID, VD, VDS characteristics are important. So why this is non-linear? Because for a small value of VDS, ID is linear, but when the value of VDS is greater, so the charge carrier concentration near the drain decreases and ID becomes non-linear. So we ends this session here. And in the next session, we will discuss the large signal model and small signal model of the transistor.